today we're going to be revising the entire module of Fundamentals of Physics. Normally A-level physics courses begin with this module, and in this video we're going to be covering units, we're going to be covering experimental uncertainties and errors, and we're also going to be covering vectors. Now let's get started by looking at units, quantities, and unit symbols. Now I have this little table over here of some quantities. For instance, we have mass. Now the unit for the mass is known as the kilogram, like so, with the unit symbol being the kg. Now the length normally has a unit of a meter, at least that's the SI standard unit, with the unit symbol being m. Time will have a unit of seconds. Of course, it can also have units of hours or any other unit. However, the SI unit is the second, and the symbol for that is just S. Temperature normally measured in Kelvin, and let's write it down in words. So that would be Kelvin. That's the actual unit, with the unit symbol being just K. Electrical current is measured in amps or amperes, and the unit symbol for that is just A. Finally, the amount of substance is the mole, and the unit symbol for that is just the mole. Now, all of those units could be assigned a prefix which has a mathematical value attached to it. For instance, tera is one possible prefix, and that has the symbol of just a T, which has a prefix factor of 10 to the 12. Giga has a factor of 10 to the 9, that's a billion. Mega with a capital M is 10 to the 6, that's a million. Kilo is 10 to the 3. Deci is a tenth, so that's just a D, and that will be 10 to the power of minus 1. Centi is a C, and this is 10 to the power of minus 2. Milli is lowercase m. Notice how mega is an uppercase m, whereas milli is a lowercase m, and that's 10 to the power of minus 3. Micro is given this symbol, and that will be 10 to the power of minus 6. Nano, which is the symbol N, and that would be 10 to the power of minus 9. And finally, we have pico, which is 10 to the power of minus 12. Now, let's revise some prefix conversions. So if we are going from a prefix to no prefix, for instance, if we're going from 5 millimeters to meters, we need to multiply by the value of that prefix. For instance, this example over here, I'm going from millimeters to meters, so I just need to times by the value of milli, which is 10 to the power of minus 3, as we can see over here. So this is just equal to 5 times 10 to the power of minus 3 meters. 700 nanometers to meters, it will be 700 nano, that's over here, that's 10 to the power of minus 9. Just seeing that my N looks a little bit like an H, so let's just change that, it's a bit better. Okay, so 700 nanometers to meters, that will be 700 times 10 to the power of minus 9. So essentially, this over here, the nano, that's just 10 to the power of minus 9. Sure, just put that into standard form. So this here will be equal to 7.0 times 10 to the power of minus 7 meters. If we're going the other way, so if we're given a value with no prefix and we want to convert it to a prefix, we're going to be dividing. For instance, if we want to go from 5 meters to nanometers, I'm just going to divide 5 by 10 to the power of minus 9, which is of course equal to 5 times 10 to the 9 nanometers. For our next example, we're converting 10 meters to millimeters, and the prefix here is milli, which is 10 to the power of minus 3. Well, once again, when we're going from no prefix to prefix, we divide by the prefix value, so this will just be equal to 10 divided by 10 to the power of minus 3, which is equal to 10 to the 4 millimeters, which is about 10,000 millimeters. The first few units that we looked at are really important in physics. They're known as the base units. So the kilogram, the meter, the second, the Kelvin, the amp, and the mole are the base units that we are going to be looking at. They're essentially like the building blocks, like the Lego building blocks of all the other units. If a unit is not a base unit, it is known as a derived unit. Let me give you an example. For instance, frequency, and you'll be familiar with this equation from your GCSEs or prior courses. The equation for that is that frequency is 1 over the time period. You will also be familiar with the derived unit of the frequency, which is just the hertz. Now, the hertz is not a base unit. It is not a unit out of this list of quantities and units that we looked at before. The base unit for from the frequency is actually determined from the equation. Because frequency is 1 over time, the base unit for this quantity, the frequency, will actually be 1 over seconds. Now in physics, we tend to write this as seconds to the power of minus 1, because in maths, any quantity raised to the power of minus 1 is equal to 1 over that quantity. Let's have a look at another example. Pressure. So pressure has a equation of the given by the amount of force by the divided by the area. The derived unit for the pressure is known as the Pascal. Now this is not a base unit. What would the base unit for pressure actually be? Well, let's have a look. First off, because pressure is force over area, and force is equal to ma divided by the area, we can say that pressure, so just write this down over here on the side, that pressure is force over area. Now the force is mass times acceleration divided by the area. Okay, well, the mass is given in kilograms. Acceleration is given in meters per second squared, so we tend to write this as ms to the power of minus 2 divided by area, which is measured in meters squared, like so. So the base unit is going to be kilograms. Now meters divided by meters squared, that's just going to give me kilograms, m to the power of minus 2, s to the power of minus 2. So the base unit for pressure is actually kilograms, m to the power of minus 1, s to the power of minus 2. Let's do another example. Work and energy that has the same unit. There are multiple equations that we could use. We could use force times distance, for instance, or sure, write down a few. So we can say that work done is force times distance, or energy, we could use a half mv squared, for instance, or we could use mgh, and these are all formulae that you guys are familiar from your GCSEs. Now all of these quantities over here that I've written down are measured in joules, and that is the derived unit. The joule is not a base unit, even if we use that in physics all the time. Now, let's see whether we can work out the base unit for the joule, and let's pick any of those equations. It doesn't really matter. I'm going to just pick E is a half mv squared because I really like the kinetic energy formula. Okay, so the base unit will be given by all of those quantities. Once again, I'm just going to write this maybe over here on the side. So the energy is given in joules. Now, what is the joule? Okay, so the half has no units. The mass is measured in kilograms, and v squared is measured in meters per second, so that's ms to the power of -1, all of it squared. So the joule is actually equal to 1 kilogram meter squared s to the power of -2, so that's going to be kg meter squared s to the power of -2. There's a term in physics that we need to be aware of, and that is homogeneous equations. This simply means that the overall units on the left side of the equation are the same as the overall units on the right-hand side of the equation. Just before we get started though, just a couple of kind of basic units. For instance, if on one side of the equation I had, I don't know, I was adding two masses. So let's say that I had total mass is m1 plus m2. Now the total mass is given in kilograms. m1 is also given in kilograms, and m2 is also given in kilograms. Now kilograms plus kilograms is actually going to give us kilograms, so this equation is homogeneous. We have to think about this in terms of units and not in terms of pure algebra. The dimensions for mass plus the dimensions for mass give us dimensions of mass, not twice that. Okay, so let's have a look at a slightly more complicated example. This is one equation that we're going to be looking at when we are doing linear motion under constant acceleration. V squared is equal to u squared plus 2as. In this equation, v is the final velocity, so that will be measured in meters per second. So over here on the left, we're going to have units of meters per second squared, and this will be equal to the initial velocity squared, which will also have units of meters per second squared. Notice how rather than meters per second or meters divided by second, I'm always writing ms to the power of -1. Anyways, plus twice the units of acceleration. Now the 2 is just a unitless constant, so I'm not going to write this down. Now the units for acceleration are meters per second squared, so it's going to be meters per second squared. And finally, the displacement is given by meters. Okay, well, let's just square everything out. So we're going to have meters squared s to the power of -2, and that will be equal to meters squared s to the power of -2 plus meters times meters is meters squared s to the power of -2. Well, this means that the overall units on the left, which are meters squared s to the power of -2, will be equal to the overall units on the right, meters squared s to the power of -2. Therefore, this equation is going to be homogeneous. Now, a really important part of physics is making estimates. Those involve making a reasonable assumption for a physical quantity or two and then using this in a calculation. Let's have a look at an example. Estimate the pressure exerted by 1 foot from an average person on the ground. We are not given any information almost in this question, so this means that we must make quite a few assumptions. So let's just write down our assumptions here. So I'm going to say that we are assuming that, let's say that the mass of the person is 70 kilograms. The assumption itself is not as of great importance as using the information in subsequent calculations. For instance, if I've chosen this to be 80 kilograms or 60 kilograms, chances are I'll probably still get full marks in an exam as long as I use this information correctly. Now, this is not really enough to answer this question because we don't really know the area of a shoe. So let's just assume that the area is, let's say, 30 centimeters by 10 centimeters. So let's just say that the area is 0.3 meters times 0.1 meters. So 30 by 10 centimeters, which when we multiply that, when they're converted in meters, so 0.3 times 0.1, it's simply going to give us 0.03 meters squared. Okay, well, let's calculate the pressure. So pressure is force over area. The only force acting in this case is mg, and because it's the pressure exerted by 1 foot, I am going to take half of that value. So half mg, because once again we are only estimating the pressure exerted by 1 foot only, divided by the area, which is, let's plug in the numbers in the next step, so divided by the area. Okay, so this is equal to a half times m is 70, G is 9.81, and I'm going to be dividing that by 0.03. And if we put this into a calculator, we're going to get about 1.1 times 10 to the 4 pascals. So right about 11 kilopascals or so, and this is our estimate. But once again, we have chosen the value, we've made a reasonable estimate for the value of some quantities, and then we've successfully plugged this into an equation. Right, on to the next bit. Okay guys, we've actually revised quite a lot about units. Now let's have a look at some of the more experimental side of things and precision and accuracy. Now when we make an experiment, we can have an idea of how precise and accurate our experiment is. In A Level Physics or in science in general, those two quantities or those two terms have a very, very different meaning. Accuracy is how close you are to the real value, whereas precision is how close the results are to each other. For instance, if I wanted to make an experiment and if I was measuring the acceleration due to gravity on Earth, the real average value for G is about 9.81, and this here is my real value. Now let's say that my experiment's value or my experimental value, let's say that that was 9.79, let's say 9.82. So let's say I repeat that experiment 3 times and I get the following results. This here is an example of high accuracy and also pretty high precision as well. So I'm going to say that this over here is high accuracy. On the other hand, if I had an experiment which, the same experiment, but I was getting the following result, let's say I was getting 8.49 meters per second, let's say that I was getting 8.52 meters per second squared, that is of course, meters per second squared, and let's say that was, my final one was 8.50 meters per second squared. Now this is an example of low accuracy because it's quite far off from the real value. However, it is high precision, So our instruments are able to reproduce a very, very similar result each time we do this experiment, so it has a high precision. Once again, accuracy is how close you are to the real value, whereas precision is how close the results are to each other. Okay, now let's have a look at errors in experiments. There are two types of errors. We have random errors, and we also have systematic errors. Now, what is a random error? Some of the key features that identify random errors are listed here. For instance, a random error is completely unpredictable. Hence the word random. For instance, it could be a random voltage fluctuation or a temperature fluctuation or an environmental factor that affects your experiment. A random error will affect the gradient of a graph. For instance, if I had a graph that should be going across here, if I had a random error here, then once I plot my line of best fit, the graph will be shifted towards that point, so the gradient will be affected. There's only one real way to reduce the effects of random errors, but the key here is that we are reducing the effects. We're not completely eliminating them, and that is to take multiple measurements. A systematic error, on the other hand, is very different. That will affect all measurements by the same amount. For instance, we could have the zero error. Should we just write down some examples? So examples include the zero error. For instance, if I had a top hand balance and rather than setting it at 0 kilograms, it is displaced by a few grams, which means that all subsequent measurements are going to be off by that amount. Or if I was to take a measurement with a ruler, not from right the end of the ruler, but from a few millimeters in, then I would have all of my measurements being off by a few millimeters. You could also have something like a parallax error where you're not looking at a measurement at eye level. This could also be a random error, by the way, depending whether you've done this to all of your measurements or not. Now, in a graph, the gradient will not be affected, however the graph will be displaced. For instance, if I had these measurements over here, and if all of those were actually a little bit higher by exactly the same amount, the graph will be shifted in a given direction, however the gradient of the graph will not be affected by systematic errors. This is really important to note. Now, moving on to uncertainties. If we are given a data set from an experiment, for instance, we have some values of G over here, we can use those to determine the absolute uncertainty in the set. The rule that we're going to use is the absolute uncertainty of a data set is equal to half of the range, where the range is just the largest value, take away the smallest value. So find the mean value and the absolute uncertainty in the following data set. Okay, well, the mean value, this is going to be quite easy. All we need to do is just add up those values and divide it by 4. And the mean value, if we do that, so let me just write this down over here. The mean value is 9.73 meters per second squared. Now, we cannot actually trust that last digit probably, because there's going to be some uncertainty in the set. Now, let's calculate the uncertainty by using the formula that absolute uncertainty from a data set is equal to half the range. So I'm going to say range over 2. Now the range is equal to our largest value, which is 9.84 we're going to take away the smallest value, which is 9.60, and then we're going to divide that by 2. Plugging that into a calculator, we're going to get 0.125 meters per second squared as our range. So we could write this value for the experiment as 9.73, and we're also going to have some uncertainty of plus or minus 0.125 meters per second squared. Now, if we are not given a data set, but instead we're actually performing an experiment, we can also find the absolute uncertainty of our reading. And the way we do that is using the smallest scale reading of that instrument. For instance, if I was to measure the length of a spring, and I do that with a standard ruler in which the smallest scale is given in a millimeter, the absolute uncertainty in this case is given by the following. So let's just write this down, that in this case the absolute uncertainty is equal to the smallest scale. Now, or the smallest reading. What do I mean by that? For instance, if our measurement was 15 centimeters, our smallest scale was 1 millimeter. So this will be equal to 15 centimeters plus or minus 1 millimeter, which is our absolute uncertainty, which is equal to our smallest scale. Typically, we would put these in the same units. For instance, 15 centimeters, that's just 0.15 meters, and 1 millimeter is plus or minus 0.001 meter. So you can see that this is actually a really precise reading. If we had a digital instrument, for instance, let's say that I had a reading of a scale which was saying, let's say 5.41 kilograms. The absolute uncertainty is defined in this case as the smallest digit on that instrument. For instance, that reading will be given by 5.41 plus or minus. Now, one of the last scale is going to be 0.01 kilograms, and let's say that we had another reading, let's say in volts, so let's say we had 2.73 volts, then we could also write this reading as 2.73, because we can't really trust that last digit. I'm going to say plus or minus 0.01 volts. Well, to put absolute uncertainty into perspective, let's talk about percentage uncertainty. Now, percentage uncertainty is defined as the absolute uncertainty divided by a value multiplied by 100. Let's calculate the percentage uncertainties for those three examples. For instance, in the first case, our percentage uncertainty will be given by our absolute uncertainty, which is 0.001 divided by a value, which is 0.15 multiplied by 100, and that's going to give us about 0.67%. So another way to write down this reading is 0.15 meters plus or minus 0.67%. So the real value could be 0.67% on one side or on the other. We're not exactly sure where the real value is. Let's do another example. So the percentage uncertainty in the case below is going to be 0.01 kilogram. This is our absolute uncertainty. We're going to divide that by our value, 5.41, and then we're going to multiply by 100. And if we do that, we are going to get 0.18%. So this is a tiny percentage uncertainty value. And this is how we calculate them. All we need to do is take the absolute uncertainty divided by the value and then multiply by 100. How do we actually combine uncertainties? Most physics formulae involve more than one variable. For instance, if I wanted to calculate the speed, assuming that the speed is constant, this is given by distance divided by time. If we had some uncertainty in d and we had some uncertainty in t, how would we find the overall uncertainty in v? Well, there are two main really important cases that we need to deal with when we're combining uncertainties. We always must ask ourselves, what are we doing with the quantities first? If we were to add or subtract quantities, we need to add the absolute uncertainties, and this is really important. If we multiply or divide, we need to add the percentage uncertainties. Here are a couple of examples. In the first case, we just add two masses and we have the following data: 5.23 plus or minus 0.01 kg and 4.33 plus or minus 0.01 kg. Find the absolute and the percentage uncertainties in your final answer. Now, because we're just adding those two masses, the overall percentage uncertainty, or the overall absolute uncertainty, will be given by plus or minus 0.02 kilograms. And this is the absolute uncertainty. And this is because we are adding the quantities, and if we add or subtract the quantities, we add the absolute uncertainties. Really important thing to mention as well is that we never subtract. Even if we were finding the difference between them, the absolute uncertainty in our answer will still be plus or minus 0.02 kilograms. Now, how do we find the percentage uncertainty in our answer after we have had the absolute uncertainty? Well, that's pretty easy. First off, the total mass, let's call it M total, is just 5.23 plus 4.33, which is equal to 9.56 kilograms. Now, we can find the percentage uncertainty in our answer, which will just be equal to plus or minus the absolute uncertainty. So it's going to be 0.02 over 9.56 multiplied by 100, which is equal to about 0.2%. On the other hand, if we were calculating our answer by multiplying or by dividing, then what we must do is add the percentage uncertainties. So let's have a look at this example. The velocity of a car is calculated using the following data. We know that the displacement d is 150 plus or minus 1 meters, and the time is 9.8 seconds plus or minus 0.1 second. Now, because we are calculating our speed by dividing the two quantities, we must add the percentage uncertainties. The first thing to do would be to calculate the speed. Okay, well, that's just going to be equal to 150 divided by 9.8. It's not 9.81, it's 9.8, like so, which is equal to 15.3 meters per second. Okay, now let's calculate the percentage uncertainties. So this will be equal to 1 over 1 50. So that's our absolute uncertainty divided by our value times 100 plus our absolute uncertainty in the time, which is 0.1, divided by our value, which is 9.8 times 100, giving us about 1.69% as our final answer for the percentage uncertainty. If we wanted to find the absolute uncertainty in our answer, I know it's not part of the question, but just for the sake of our understanding, all we need to do is find 1.69% of 15.3, which is about 0.258, let's call that 0.26 meters per second. So a way of writing our final answer out will be 15.3 plus or minus, or 15.3, let's include the unit, meters per second, plus or minus 1.69%. And yet another way would be 15.3 plus or minus 0.26 meters per second. So just to summarize, if we are adding or subtracting quantities, we add the absolute uncertainties. If we are multiplying or dividing quantities, we add the percentage uncertainties. We never ever take away uncertainties. We only add them. The question is, which ones do we add, absolute or percentage? One more case though, which is quite interesting, is that we can raise a quantity to the power. For instance, here we calculate the percentage certainty in D. We may have a formula that involves D cubed or squared or raised to the power of 17, etc. For instance, if I had I given by 5, the current, so we've measured the current to be 5.0 plus or minus 0.1 amps, what is the percentage uncertainty in I squared? Well, the rule that we're going to use in this case is that if we raise a quantity to the power of n, the percentage uncertainty in that quantity, just call it y, to the power of n, is equal to n times the percentage uncertainty in y. In other words, we kind of just bring that power down here and then we multiply. So let me just give you an example. Our percentage uncertainty in y squared, we could find that pretty easily. All we need to do is find the percentage uncertainty in I and then multiply it by 2. So what I'm going to write is the percentage uncertainty in I squared is equal to twice the percentage uncertainty in I. In an exam situation, you don't need to write out those steps. You could directly just multiply it by 2. But for the sake of being thorough and just going over everything and making good notes, I will be just writing those down in my digital notes. Okay, so this will be equal to 2 times 0.1 divided by 5.0 times 100, which is equal to 4%. So the percentage uncertainty in I squared is 4%. Now let's have a look at how we could determine the uncertainty from a graph. We have a few data points over here for a graph of voltage against current. Now notice that across the y-axis we have these things called error bars. Now an error bar tells you the absolute uncertainty of that measurement. For instance, the voltage measurement of this point will be uncertain within 1 volt. We know that the real value is somewhere here. So for this measurement in particular, we could write this down as 3 volts plus or minus, or this actually has a huge absolute uncertainty. So notice it could be anywhere from 3 to 4 or from 3 to 2. So this will be 3 plus or minus 1 volt. The way we can determine the percentage uncertainty in our gradient is by drawing the line of best fit and also drawing the line of worst acceptable fit. Let's do this. So first off, to draw the line of best fit, all we need to do is just make sure that we go through all of those data points as close to the center as possible. So in this case, this will be our line of best fit. And I could just write this down over here, that this here is the line of best fit. Now, to draw the line of worst acceptable fit, the rule that we're going to use is that we're going to start at the bottom of the bottom error bar, and we're going to go from to the top of the top error bar. So in this case, our line of worst acceptable fit, which I'm going to just draw in blue, will look something like this, where this is the line of worst acceptable fit. It starts at the bottom of the bottom error bar and goes to the top of the top error bar. And I'm just going to label this as the line of worst acceptable fit. Keep in mind that there are two possibilities for the line of worst acceptable fit. You could also equally have gone from the top of the bottom error bar to the bottom of top. However, it's just a little bit easier to remember bottom of bottom to top. So why did we actually draw the line of worst acceptable fit? Well, we're interested in the percentage uncertainty in the gradient, and the formula for it, which is not given in the exam, is that the percentage uncertainty in the gradient is equal to the gradient of the line of best fit, take away the gradient of the line of worst fit, divide by the gradient of the line of best fit, times 100. I'm just going to add in some brackets over here just in case. And this is a really important formula. We could use that if we wanted to calculate the percentage uncertainty in our gradient in this case. Okay folks, so this was part 1 of a revision lesson in which we've covered all of units, errors and uncertainties. Join us for the second installment of this video in which we're going to be looking at the whole of vectors required for A-level physics. Hopefully this was useful for your revision. Thank you very much for watching, and I'll see you in the next video.